Hello everyone, and thank you for attending today's webinar, More PRIAS Examples in OM EBSD Analysis. Before we begin, we want to cover a few housekeeping items. At the bottom of your audience console are multiple application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget at the bottom and submit your question. We will try to answer these during the webcast, but if a fuller answer is needed or we run out of time, it will be answered later via email. We do capture all questions. A copy of today's slide deck and some additional material are available in the resource list widget that looks like a green folder at the bottom of your screen. You can expand your screen area by clicking on the maximum icon at the top right of the slide area or by dragging the bottom right corner of the slide area. If you have any technical difficulties, please click on the Help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent for you earlier. Now I'd like to introduce myself. I'm Dr. Patrick Camus, the Director of Research and Innovation at EDAX. Today I'd like to show you a few examples of PRIAS imaging and options. PRIAS is an imaging method that can be used when performing EBSD analyses in an SCM. EDAX has presented a previous webinar on PRIAS that described much of the technical background on this imaging technique. I will review a little of that background now so that new viewers to the technique can follow the rest of this webinar. The majority of this webinar will examine the benefits of using PRIAS to produce a variety of images for fine detail structural characterization during EBSD analyses. During an EBSD analysis, the electrons emit in all directions from the sample surface. These electrons will contain information about the interactions that they incurred while traveling within the sample. Different detectors are sensitive to different sample interactions. For instance, the secondary electrons are highly sensitive to the surface topology, as in traditional SEM imaging. A hardware forescatter detector is sensitive to atomic number, crystallography, and topology. The IQ map in EBSD is a calculated image based on the crystallographic signal. In addition, the camera intensity can be used as a detector to investigate the emitted electron signal. The crystallographic signals are usually produced by diffraction within the sample. The intensity emitted from the sample is directly related to the orientation and perfection of the sample crystal structure. Most users are most familiar with this imaging method in light microscopy or transmission electron microscopy, TEM. A bright field image is produced by placing an aperture around the transmitted beam and excluding all diffracted beams. A dark field image is produced by placing an aperture around the diffracted beam and excluding the transmitted beam and all other diffracted beams. In EBSD, there is no transmitted beam, and the diffraction is not spots but bands, but the same ideas apply. Furthermore, since there is significant intensity at all angles, most aperture locations can produce images. Samples are usually mounted for EBSD for the majority of the electron intensity to hit the phosphor screen to maximize the signal for the orientation analysis. The usual location for hardware diodes for electron detection is below the screen as illustrated here, but any location around the screen is possible. The disadvantage of this arrangement is twofold. One, these locations are not optimum for intensity, and two, the hardware locations are fixed, unlike TEM dark field locations. However, there is no restriction that only the hardware signal can be used to construct the image. The intensity on the screen can also be used. In addition, there is no restriction that the intensity of the whole screen needs to be used. Any location can be used, like the red circle in the figure, which more closely mimics other dark field imaging techniques. I like to describe this method as using a virtual aperture. A disadvantage of this technique is that the screen intensity is measured using the EBSD camera pointing at the screen. Let's look into some virtual aperture geometries in more detail. The first choice is to use the whole screen as the aperture. The advantage is that the signal is high, so the noise is low. The disadvantage is that the contrast is also low, but not necessarily zero. Although possible, this method is not very useful in practice. The opposite extreme is to use a single pixel for the virtual aperture. The advantage are easy placement, many possible selections, and potentially high contrast. The disadvantage is that the signal may be so low as to void any benefits. This option is not too useful in practice. Somewhere between these options is a selection of a virtual aperture of a finite size. It has the advantages of high signal, low noise, reasonable contrast, ease and number of selection. This is the general direction that the software was developed. To make the location selection slightly more reasonable and reproducible for most users, we have included a number of predefined aperture options. There are a number of location options available, like 3x3 adjustable, 5x5 fixed, 3 fixed, and multiple user-defined. This slide shows the location option for a 5x5 fixed grid of potential virtual apertures. The display shows the location of the virtual apertures on the screen and the resultant dark field image for each virtual aperture. Any of these can be selected individually, or any number can be selected either positively or negatively to provide the desired image. When looking at these images, it is clearly evident that they contain contrast related to the location of the virtual aperture on the screen, as experienced in other dark field imaging techniques. This provides the user with complete flexibility in selecting the location that provides the needed contrast for structural interpretation. Exploiting the user-defined aperture option, total flexibility is provided the user in selecting both the size and shape of the virtual aperture. Although not usually chosen, this method is unique in that other dark field microscopes use physical apertures that are typically round in shape. This option has been found to reduce the intensity of unwanted contributions to the image contrast. EDX has named this software option PRIAS. It is available both during EBSD experimental setup, when the user would acquire the preliminary electron image of the sample, and during the post-acquisition analysis if the camera patterns were saved. The advantage of the live option is that the dark field contrast can be absorbed before the time-consuming acquisition takes place for confirmation of the correct acquisition location. The disadvantage is that the EBSD camera must be used for the image, and the acquisition speed is comparable to a slow-scanned electron image. The post-processing method has many more processing options for optimizing the image contrast, but requires creation of large files containing the diffraction patterns at each pixel location. The virtual aperture method used for the following examples is the simple but effective 5x5 fixed. This option provides enough variety in the locations to find images containing nice contrast. This example shows that the small angular change between adjacent apertures can significantly change the contrast in the image. It also shows that the contrast changes in all directions as different regions of the diffraction pattern are probed. The intensity and contrast in the image depends on the contributions to the intensity within the selected aperture. There are a number of intensity contributions. Since the primary analysis technique is diffraction-based, we expect the principal contribution is diffraction contrast. This consists of both crystallographic orientation contrast and strain or crystal deformation contrast. These contributions are the signal that should coordinate most with the basic results of the EBSD technique. However, there are additional contributions that may be important or might complicate the analysis. These include the backscatter coefficient and atomic number contrast. The primary backscatter contrast arises from the well-known distribution of backscattered electrons from a solid. It may contain interesting information, but only in selected circumstances. The distribution of the backscatter coefficient can also be modified by the surface structure of the material. This contribution provides information on the smoothness of the surface, which may be important for the study or may be a complication. The atomic number, or Z contrast, is usually an important piece of information and can be used in coordination with any X-ray signal that is collected. Selection of different apertures can be used to enhance or reduce these contributions as needed. For instance, these two images from the same data set show enhancement of Z contrast and topological contrast by judicious selection of aperture locations. Z contrast is enhanced when selecting apertures at the top of the screen and reduced for lower apertures. Topological contrast is enhanced for lower apertures than for higher apertures. The flexibility in selection of the location of the apertures provides flexibility in providing results that aid in the proper interpretation of the sample analyses. The orientation contrast PRIAS maps usually have a contrast that is consistent with the EBSD results. They can show boundaries and grain intensities that mimic the EBSD IQ maps. In the RGB color mode, they can show grain images that seem identical with EBSD IPF maps. However, the color in these maps are not quantifiable and do not correlate directly to an orientation. This example also shows that the PRIAS images can be produced both live before the EBSD map acquisition and produced later from stored EBSD diffraction patterns. When the deformation or strain becomes greater, the contrast within grains may increase. This figure illustrates how the strains are slightly deforming the crystallographic planes within each grain. This imaging technique is extremely sensitive to small amounts of deformation. Unfortunately, at this point in the understanding of PRIAS contrast mechanisms, the strain cannot be quantified from the contrast in these images. If the surface of the sample is not smooth, the 3D angular distribution of the backscattered electrons will be distorted from pixel to pixel, leading to contrast in the image. In this example, the secondary electron image shows a patterned surface, which leads to a patterned PRIAS image using certain virtual apertures. This contrast is not related to the orientation or strain within the sample, although that conclusion could be hard to prove in isolation. When the selection of a different PRIAS aperture is chosen, that topological contrast is reduced and the true orientation and strain contrast in the sample is presented. The flexibility in choosing the virtual aperture in PRIAS helps in the correct interpretation of the contrast in the image. Without the flexibility of viewing multiple images using different apertures, the wrong conclusion may be reached when forced to use a single aperture, like for a hardware forescatter detector. Other less frequent contributions can also be observed. In this example, magnetic domains can be imaged in a few of the virtual apertures. The images show the usual features of aligning with the 100 planes and are continuous across the grain boundaries. There is a different imaging method that is unique to PRIAS and cannot be duplicated by hardware forescatter detectors, the differential images. In this method, the diffraction patterns of two consecutive pixels are compared and the amount of difference between them is displayed. The resultant figure typically highlights grain boundaries. The PRIAS boundaries match very closely with the EBSD grain boundaries shown for reference in color. In the following examples, various PRIAS images will be compared to EBSD maps to see complementary features. In this set of images for an annealed nickel sample, the PRIAS grains compare nicely with the IQ and IPF grains, and the differential boundaries compare nicely to the grain boundaries. A specific similarity in the IPF, IQ, and PRIAS maps are the uniformity of the contrast within the grains, indicating the lack of deformation within the annealed material. A similar comparison on this fine-grained material shows the same similarities. However, they are much harder to see in these small images. Only when the maps are viewed at 1x or larger can the very subtle details become evident. Twins are visible in materials when a reflection occurs along specific crystallographic planes in a crystal. They are very evident in IPF as planar boundaries between grains. In cubic materials, they occur at 60-degree misorientation and are colored as red in these boundary images. The PRIAS and differential images clearly show and coordinate with the boundaries shown in the grain boundary maps. An interesting side note is the sensitivity of the PRIAS differential image to the carbon contamination from a previous acquisition that appears. Sometimes contrast mechanisms are produced from an unexpected source. In this data collected from a paper staple, a high amount of deformation is expected and is observed in slight variation in color in the IPF and graded contrast in the PRIAS. The grain boundaries also appear slightly blurry from the deformation and the small grain size of the material. Although difficult to see, there is a high correlation between the IQ and the difference images. In this annealed sample, we expect minimal contrast within the grains and highly concentrated contrast near the indentations from the deformation. The deformation contrast is difficult to see in the IPF, but it is there, but it is very easy to see in the other displays. The benefit of PRIAS is that it is the only method to see this deformation structure live without performing the whole EBSD acquisition. In this example, subtle contrast is found in all of these images and maps, which indicates subtle deformation within the grains. I like this example in particular because it reminds me of the similarity of the diffraction contrast in PRIAS and that found in TEM images. The central grain in the PRIAS image has a feature which is commonly referred to as a bend contour in TEM. In the future, the contrast in the PRIAS images might be quantified and predicted using similar methods to TEM image contrast. Electron image contrast can arise from many sources, either expected but also unexpected. Different virtual apertures can isolate or remove unwanted contributions so that the correct contrast interpretation can be made. Pattern difference images provides a unique grain boundary image that hardware forescatter detectors cannot provide. PRIAS virtual apertures provide more flexibility to obtaining the correct contrast interpretation than simple hardware FSDs. I thank you for attending this webinar on PRIAS imaging. I will now answer any questions that are submitted. Thank you very much, everyone, for sitting through the webinar. If you have any questions, feel free to submit them into the Q&A. We have one there that came in a little bit earlier. What are the sizes of the PRIAS images? Any number of pixels can be used for the images themselves, depending upon what the software options are that's selected. So if it's the pre-scale, it's the whatever number that you collect for the electron image. If it's the post-acquisition, it's whatever the size of the OIM acquisition that you run. Typically, it's 256 or 512, but it could go higher or lower as needs arise. Another question came in. Do I need to change any EBSD acquisition settings to optimize the images? Not really. You just have to use your current settings and enable the pattern storage to look at the PRIAS post-acquisition images. The live images, usually it's optimized that you go to the highest binning possible and limit your number of pixels to go. It depends on the speed of your camera and the total number of pixels, so you really need to have the camera operating very, very quickly in the live mode to do that. Another short question, how long does it take to collect the live? The live image does take a little bit of time to collect. It would be similar to what you would do for a slow scanned high quality SEM image. So typically 30 seconds is a minimum amount of time depending upon how many pixels that you have and the speed of your EBSD camera. Could go upwards of 1.5 minutes or 2 minutes depending upon what the quality of your sample is and the intensity coming off of your sample. Question came in, would there be any concern if the acquisition map is done at the edge of a metal or the sample where we notice a shift in the electron beam? I don't think there'd be a primary concern. You will detect the signal that you will detect that comes off, that gets emitted off of it. There could be some distortions introduced if there are distortions in the electron beam, let's say due to charging of the mount to the side that deflects the beam. There could be some distortions, but that intensity will still go on to the phosphor screen. You might be able to avoid that by using certain virtual apertures that are away from that charged region, so you could minimize the effect of the charging in those regions by using apertures farther away from those regions. Are there any recommendations for which areas of the 5x5 regions to choose for optimum information? No. We do have some general guidelines that the top of the image tends to be more Z contrast, the bottom tends to be more topological contrast, but besides that, there's not one sweet spot like the position that would be like a 3-4 position. That's optimum for every sample. We haven't found that that's the case, as you notice through a variety of the examples in the presentation. The selected aperture was quite different between each one. Every sample is a little bit different, provides a little bit different intensity coming off of the sample going to the phosphor screen, and in that case, the contrast mechanisms and the contributions from the different mechanisms actually affect quite markedly what the images are. So that's the one advantage, is you do have all 25 of those images,
and it's easy to click on each one and survey what each one is and see if it has the contribution that you're looking for or excludes the contributions that you're not interested in. But not one aperture does not fit all. How do we know the zone axis of each domain? This technique does not deal with the quantification of the orientation. It only quantifies the electron intensity in those regions. To obtain the zone axis for each of the pixels in the image, you actually perform the full-blown EBSD analysis by collecting high-quality diffraction patterns and matching that to the crystallographic information provided to it, and then it will calculate the orientations. This technique is only an imaging technique, which correlates with the diffraction information, but it does not measure the diffraction information in and of by itself. Is it possible to do simulations according to our known structures? You can do simulations and get the zone axes. I have not seen anyone try to do imaging of simulated maps, for instance, to see what the PRIAS images are. That would definitely be a next step in the theory of the PRIAS imaging, is to go back to simulations or models and the basic theory, similar to what is done in transmission electron microscopy and diffraction contrast in that technique. The spatial resolution is intrinsic to the EBSD technique, so it's whatever the spatial resolution is of the technique. We do not claim that you have higher spatial resolution than what has been predicted earlier or shown earlier in any of the techniques. To get higher spatial resolution, obviously you would like to have a field emission gun to do it, and then you would need to go on a very fine scale, stepwise, but this technique is just an imaging technique related to the basic EBSD physics, so the spatial resolution is the same. I didn't notice it, mention it directly in the presentation, but this technique is easily applicable to transmission EBSD, which has obviously a higher spatial resolution for the diffraction information than the traditional bulk EBSD technique. But this imaging mode does not have increased resolution as far as we can tell compared to what your standard resolution is for the technique. Are there any other questions that we have? It has come back as a note that there was a attendee today that mentions that they actually used the PRIAS imaging in transmission mode on atom probe tips. So you could use that and get the determine where the grains were from that to give an additional imaging technique for locating where the grains and phases are in atom probe tips by using transmission mode. What are the limitations of the technique? Pretty much the basic limitations that you have with EBSD. You need to have at least reasonable quality diffraction patterns coming off. We have noticed that you can get slightly more information out of the PRIAS imaging than you can, qualitative information out of the PRIAS imaging than you can out of some of the EBSD orientation quantification images that you can get out. So you can run slightly worse samples and get somewhat reasonable PRIAS images, but obviously these are not quantified. To do the quantitative diffraction, you need the high quality patterns. Besides that, we haven't really found too many other limitations. The only other one would be during the live acquisition. It is a little bit slower than some electron detection than, for instance, a secondary electron detection. It would be a little bit slower acquisitions, usually needing 30 seconds to 2 minutes to collect. Those are the main limitations that we found. Are there any other questions? We will stay on the line for a few more minutes. Okay, not seeing any more questions coming in. I thank you all once again for your attendance. I hope that the content in the webinar was helpful for you. I hope the questions answered a few things that I may have left out. And once again, the presentation will be available in a couple of days for download. Thank you very much and have a good day.